Okay,
Hey,
Randy,
Randy,
can we
can we
start
start
soon?
soon?
It's fine.
It's fine.
Absolutely, yeah.
Okay, I will
I will
introduce you
introduce
first
you
then.
first then.
Just give me
Just
time.
give me.
Sounds good.
Okay,
Okay,
everyone,
everyone,
let's start
let's
then.
start then.
So the
So
sound
the
box are
sound box
not
are
so
not
good.
so good.
What's going?
What's going?
Let's see.
Let's see.
Why
There is echo.
Hello?
Hello,
Can you hear?
can you hear?
There is
Ah,
some echo. Give me a
give me
second,
a
friend.
second, friend.
Hello?
Hello,
Hello?
hello.
Alô? Tá com eco? Não, né? Parou. Okay. Sorry for this, Randy.
Nope, no
Okay,
problem.
everyone. So let's start. so it's a great pleasure to have Professor Randall Beer in our school. So Professor Beer is currently a professor of informatics and computing and directs the NSF IGERT training program in dynamics of brain-body environment interaction in behavior and cognition at Indiana University. He received his PhD in computer science in 1989, and from 1989 to 2006, he was a professor of electrical engineering and computer science, biology, and cognitive science at Case Western Reserve University. He spent the 1995 to 1996 academic year as a visiting scientist at the Santa Fe Institute, where he also served as external faculty member for the next 6 years. Broadly speaking, Professor Beer's research concerns how organisms operate as integrated wholes, with a particular focus on how behavior arises from the interaction between brains, bodies, and environments. More recently, his work has focused on developing a rigorous theoretical characterization of the key ideas underlying Maturana and Varela's biology of cognition and enaction frameworks. Professor Beer's work has influenced a generation of researchers in neuroscience, cognitive science, and behavioral science in general. And more broadly, anyone interested in understanding cognition has read his work. I myself was strongly influenced by his seminal papers on the relevance of studying interaction of body, brain, and environment. Without further delay, please, Randy, the floor is yours. Thank you.
Thanks, Daniel. And I wanted to thank all the organizers for inviting me, and I apologize for that I couldn't be there in person with you. So, as they say, I think this talk is going to be, and now for something completely different. I want to try to directly tackle the entire theme of the school, the origins of life, behavior, and cognition. And in particular, I'm going to try to sketch out what a theory of life, behavior, and cognition might look like, not in our universe, but in a simplified toy model universe, where we can actually work out theories in great detail and to the point where we can calculate things. The lectures are broken into two parts. The first lecture is going to focus on a theory of constitution of emergent individuals, which roughly speaking is about concerned situated embodied dynamical perspectives on cognition and behavior, and in particular the study of brain-body environment or agent environment systems. But I decided not to talk about that today. Instead, I want to focus on the fact that we generally take this agent environment split for granted. We don't ask, how do we know where the agent ends and the environment begins? We just assume we have an answer to that question. But I'm interested in today in what is the agent in this picture and where does it come from? Where does that agent environment split come from? And my standard strategy for sort of tackling these kinds of, I don't know, conceptual sort of theoretical questions looks something like the following. I usually start by selecting some theoretical framework or conceptual framework that I think might have something interesting to say about a question like this. Then I try to develop one or more toy models according to the principles of that theoretical framework. Then try to build theories of those toy models with respect to the framework. and then try to calculate things with that theory and ultimately evaluate its utility. And once I've been through that once, there's typically a feedback loop where we refine things. So um, if the theory doesn't do a very good job explaining the toy model, then we may have to revise the theory. If the toy model fails to capture some of the key features of the framework that we were interested in, we may need to come up with a new toy model. And if after constant revisions of our theories and toy models, the framework just doesn't pan out, then maybe it wasn't such a great conceptual framework to begin with. So I'm going to be drawing, as again Daniel mentioned, on Umberto Maturana and Francisco Varela's Biology of Cognition framework. That's going to be the theoretical conceptual framework I begin with. For those of you that don't know them, Maturana and Varela were Chilean biologists interested in the nature of life and cognition. And their biology of cognition framework basically proposed a conceptual way to bridge from physics and chemistry to biology and from biology to behavior and cognition. And it's kind of founded on two core ideas we're going to be talking about: autopoiesis, which is sort of a sketch of a theory of constitution, and structural coupling, which is a sketch of a theory of interaction. And our topic for the first lecture is mostly going to be autopoiesis. Our topic for the second lecture is mostly going to be structural coupling. So this framework was later extended by Varela to become what's often called the enactive framework, where he kind of generalized autopoiesis into what he called autonomy, and he generalized structural coupling into what he called enaction. From my perspective, the biggest drawback of this framework is that it's basically a verbal framework. It's conceptual in nature. It doesn't have a rigorous formal characterization. And in fact, although Varela tried quite hard in part of his career to develop a more mathematically formal characterization, Maturana largely rejected formalization as not being a useful thing to do with these ideas. But my goal is going to be to try to flesh out this framework in enough technical detail so that we can evaluate its take on this question of what is an agent and how does it arise. Okay, the next step in my strategy was a toy model. And the toy model I chose for this work is actually the game of life cellular automata that was invented by John Conway in the 1970s. So basically, this universe consists of a two-dimensional grid of cells that can be in one of two states. And everything that can happen in this toy model universe is completely determined by a single universal dynamical law, which I've written in this way. And the basic idea behind this dynamics is as follows. If you focus on a small piece of this binary lattice and focus further on a single cell in that lattice, like this yellow one, and we count up all of the surrounding cells in that cell's neighborhood that are on, and we record that information. In this case, the yellow cell has 3 on neighbors and 5 off neighbors. Okay. We do this for the entire universe, basically, and that gives us essentially a field of neighborhood counts. And that's essentially what this term, can everybody see my pointer?
We can see. Mhm.
Great, great. Okay. So that's essentially what this operator is here. It takes a field and basically returns a neighborhood count field. And then we compare that neighborhood count in one of two ways. For every location that has a neighborhood count of 3, then if we just use the delta function here, that will return a 1. And so that cell will be on in the next generation of this dynamics. For every cell that has a neighborhood count of 2, and furthermore, it's currently on in the present time step, that will be on in the next generation. Otherwise, the cell will be off. And so applying that rule to basically every cell in the grid gives us a new state. And we can just iterate that over and over and over again to look at the evolution of the state of this toy model. So Conway didn't have this in mind when he designed it, but after all, it's just a model. We can interpret it any way we want. I want us to think of this as a kind of physics. Obviously, nothing like our physics in the real world, but nevertheless, a kind of physics that's governed by essentially a universal law operating on a field of configurations of this universe to produce new field of configurations. If we step up one level to think about this toy model, we find that this toy model can also support a kind of spatial chemistry. And here is what I mean by that. So if we consider local arrangements of components like this arrangement here, we can think of groups of these components, spatially organized groups, as triggering processes that are given by the Conway physics, given by the underlying dynamical law, but now we're looking at spatially structured subsets of that. So we can think of that these groups of components triggering reactions, triggering processes that produce new groups of components. And it's not just this group, it's all the groups that show up in here locally. So there's another process here that produces another product here. And in general, we have 512 possible reactions, but there's a lot of symmetry in the game of life. And so we actually only have 102 symmetrically distinct classes. And these are broken into basically 5 possibilities: a null process, a production process, a destruction process, and then maintenance processes that just maintain a 0 or 1 state. And here I'm giving you examples of each of these, and then I'm introducing a notation for processes, which basically color the central cell according to whether or not this process will produce a new component, it will destroy an existing component, or maintain a component in its current state. Okay? So we can think now from the point of view of this spatial chemistry of the universe as being filled with processes. Okay? And both these processes and the reaction networks in which they engage are ephemeral. This is going to be very important. So these processes come into being, they come into existence, they interact with other processes in reaction networks, and then the processes may disappear or new processes may replace them. So it gives us a dynamic spatial chemistry that's ephemeral in nature, and that's going to be very important. So I want to think of this as a kind of chemistry that we can implement or observe in the Conway physics. Finally, and this is going to be the biggest leap, so this is what the whole talk is going to be about. If we step back even further and just look at the time evolution of game of life universes, we see these persistent spatiotemporal patterns that come into existence, persist for a while, and then may disappear. And some of these patterns are static, some of them are dynamic, some of them are ambulatory. And the question I want us to ask is, to what extent might it be interesting to think about these entities as a kind of biological individual in this toy model universe? Now, our intuition would say, wait, this has nothing to do with biology. These aren't alive. And that intuition has a lot going for it. But the fact of the matter is, to really answer the question, we need a theory. We need to spell out what a living system is, and then be able to apply that theory to this toy model and say, well, you're right, these don't constitute biological individuals. Or, according to at least this theory of what a biological individual is, this might constitute one. Okay? So there are a couple of different approaches that people generally take, often implicitly in biology. So one common approach is to focus on the components out of which a system is made. So the most common elements of life on Earth are hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Or if we don't focus on elements, but focus on the molecules that we build from these elements, we get these different classes of molecules that play major roles in biochemistry, like carbohydrates and proteins and lipids and nucleic acids. Okay? So one idea would be basically to say, well, a system is living if it's made up of the same kind of components as our notions of living systems in the terrestrial sphere. But this is a little problematic as a definition, because it effectively disallows any other chemistry by definition. Okay? Imagine if in 1950 we all agreed to define automobiles in terms of the steel from which they were built and the gasoline-fed internal combustion engines that powered them. Okay, well then what would we make of a modern electric vehicle that's built from composite materials. It seems like focusing on the specific chemistry that underlies the instances of living systems that we're most familiar with is too narrow. It's too specific. So another idea is to focus on a basically laundry list of characteristics that living systems possess, like metabolisms, homeostasis, growth, irritability, reproduction, and evolution. Okay. Typically, many people place the strongest emphasis in this list on reproduction and evolution. But this is also a little problematic. Surely reproduction and evolution are very important to biology, but there are certainly non-living things that reproduce, and there are living things that do not. So, for example, most mules are sterile, but surely they are alive. Okay? So laundry lists also have their limitations. Well, what else is available? Well, this is where Maturana and Varela come in. They basically put forward a different kind of proposal about what a living system is. Rather than a list of components or a list of characteristics, they said living systems are a particular class of organization of processes. Okay, and they called this class autopoiesis. Auto from the Greek root meaning self, and poiesis from the Greek root meaning creation. So autopoiesis is a neologism basically meaning self-creation. And their definition, which I will present here, is as follows, an abbreviated version. An autopoietic system is a system organized as a network of processes of production, transformation, and destruction of components which satisfy two conditions. One is through their interactions and transformations, continuously regenerate and realize the network of processes that produce them. And two, this network constitutes the system as a concrete unity in the space in which the components exist by specifying the topological domain of its realization as such a network. And they call these two conditions, well, these two conditions are referred to typically as a self-production condition and a self-distinction condition. Now, I don't know about you, but on first reading of these statements, it's a little difficult to understand exactly what they're getting at. And part of my task today is to try to flesh out in great detail what they might mean in the context of this toy model. But before I do that, let me start with an analogy, which I think can help. So let's think about a factory. A factory is a system that takes in raw materials and produces some sort of products and also waste materials. Okay? However, factories are physical systems, and components of those factories will break down over time if they're not maintained. So how does a factory go about replacing worn out parts or fixing things and so on? Well, typically they appeal to other factories that produce the kinds of things that they need to continue their operation, like, I don't know, a new press or something, okay, a new painting machine or spot welder on an assembly line. But almost any modern factory does something else too. Typically, this factory itself has certain capabilities for producing things. And if they have that expertise and materials and tools in-house, so to speak, then they can devote some of their resources to their own maintenance, rather than having to go out to another factory and bring things in, which is slow and can be expensive and so on. And in doing so, they may be slightly less efficient at producing products because some of the raw materials and some of the energy and activity in the factory is devoted to its self-maintenance, but they also are saving money and time in maintaining the factory itself to some extent with its own processes. Well, we could take this to its logical conclusion. Imagine a factory that devotes all of its resources to keeping itself functioning. So now it produces no actual product other than itself. It just takes in raw materials and produces waste, but in the process, it maintains the continuing operation of this factory. It is a factory that makes itself. And pretty much that's what Maturana and Varela are trying to capture with the notion of autopoiesis, that living systems are factories that make themselves. Okay? So let me try now and cash out that idea in a little bit more detail by looking at each of these conditions in turn. So the first condition is a self-production condition. most sets of Conway physics or Conway chemistry processes produce components that trigger a different set of processes. So here we have the same set of components I showed you earlier. They trigger processes like these two, which produce new arrangements of components. And if we continue this forward in time, this arrangement would generate processes that are different from this set of processes, which would in turn produce different arrangement of components. And this thing would just sort of go on. But some arrangements of components in the game of life, in this spatial chemistry, trigger processes that produce components that trigger the exact same set of processes. Okay? So you basically get situations that maintain themselves. And we can think of this in a couple of different ways. One way is that special configurations trigger special processes that, operating in conjunction, actually regenerate those triggering components. Or, and this is the way I'm going to do it, is we can sort of subordinate the notion of components and just focus on the structure of the processes. So basically, we get these dependency networks of processes where this process, in this case, is one maintenance process. It maintains a component that plays an important role in enabling this process, and this process. And likewise, these other three processes maintain a component that play an important role in triggering these other processes, so that collectively, these processes persist by essentially maintaining the conditions that each of them requires to persist in such a way that is mutually supporting. The entire set becomes self-sustaining, and it has a particular organization, a particular network of interdependencies with respect to the underlying chemistry that is invariant. Okay? One thing I want to stress here is it's not just the products that the processes produce that are being maintained, it's also their spatial arrangement. If you just produce a random set of processes and sprinkle them spatially around the game of life universe, you won't get this self-sustaining property. They have the right components have to be produced in the right locations so that they trigger the processes that will continue to reproduce, that will continue to maintain that invariant structure, that self-sustaining nature. All right, what about the self-distinction condition? Let's focus on this same arrangement of components. In game of life parlance, this is referred to as a block, this 2x2 square of on cells. It's the simplest persistent structure in the game of life. So if you ask a game of life enthusiast, what is a block, they would draw this picture. But I want to point out that that definition of a block is lacking certain essential things if we want to try and apply the notion of autopoiesis to it. So first issue I want to bring up. How many blocks are in this configuration? You could argue that there are none, because there are no isolated 2x2 configurations. You could argue that there's one big block that's now 4x4 rather than 2x2, but it certainly has similarities to the block. You could argue that there are four, so each corner is a 2x2 block. Or you could argue that there are 9 if you allow one block's components to overlap with the next block beside its components. Okay? So this notion of a 2x2 set of one cells divorced from any surrounding information doesn't make a very good definition of a block. Another second reason why it doesn't make a very good definition is no matter if you answered yes to any of those ideas I just suggested about where the blocks are in this picture, you have the following problem, that if you run this configuration under the Conway physics or the Conway chemistry, what you get looks like this. That is, none of those definitions of a block generalized from here to here actually persist the way blocks do. Okay? So dynamically, no definition of a block here makes any sense. And finally, if we look from the point of view of the processes going on that maintain a typical block like this one, what you'll see is that there are these one maintenance processes but there's also a set of zero maintenance processes that surround it that are non-null processes. Okay. And these zero maintenance processes are also essential to the operation of a block. Okay. So from those considerations, we are kind of forced to define a block to be this, a 4x4 configuration of components with a 2x2 set of one cells at its core, surrounded by a ring of, or a boundary of off cells. And the mutually supporting interactions between these one maintenance processes and these zero maintenance processes are required for the block to persist and behave as a block. Okay, because those zero maintenance processes out here are enabled by the one maintenance processes, and the one maintenance processes depend for their operation on the zero maintenance processes. Okay, so we end up with a full block organization that looks like this. It contains the core of the earlier block organization, that is the mutual interdependence between these one maintenance processes, but it also includes this necessary boundary that separates what is a block from the environment that surrounds a block. Okay. So, at least tentatively, if you follow the argument I've just sketched, a block seems to satisfy both the self-production and the self-distinction conditions, or at least an interpretation of them, because they're verbal, so we could quibble about interpreting each term in Maturana and Varela's definition, but this is an interpretation that can be consistently applied to this really simple block. Let's test this idea now by seeing if we can apply it to more complicated kinds of entities in the game of life. And in particular, I want to focus on what's called a glider. A glider is basically the simplest motile entity in the game of life. Okay, and this just shows it kind of wiggling its way across the environment, changing its location, changing its configuration, but maintaining its identity as a particular sort of collection of components. Okay. If we look carefully at how this works, we'll basically see that gliders go through a recurring force cycle. So if we start here in this configuration, this one goes to this one, this one goes to this one, this one goes to this one, and this one comes back to the same configuration, but offset diagonally one cell to the right and down. Okay, and that will keep repeating. This one will trigger an analogous offset version of this, and so on. This cycle just keeps repeating. That's what a glider is in terms of just thinking about component configurations. But what we did looking at the Glock was not focus on components, but focus on processes. So this is what a glider looks like from the point of view of processes. And this is where that ephemeral nature of processes matter. Notice that which processes are active at any one time in a glider changes from moment to moment. Okay? But there's still a persistence in that this set of processes repeat after 4 steps. And to make that explicit, let me just draw them out. So this configuration enables this set of processes, which creates this configuration, and so on, all the way back around until we get this set of processes enabling producing this configuration, which, although it's not the spatial embedding of this configuration is different, it actually enables the exact same set of processes. Okay? And from that, we can extract this dependency network. It's a little more complicated now, but I'm going to take you through the steps to show you that this can be done. So let's focus on one particular set, a 3x3 set of configurations that are part of a glider in this configuration. Okay? That process is this. Okay? This enables or triggers a production process from our set of processes. If you just look it up in the table of processes that I sketched earlier, this is what gets triggered. That process produces a one cell. In fact, it's this one cell of this configuration. Other processes are triggered by other configurations here and produce other components of this configuration. And this new component, in turn, plays a role in triggering all 9 of these processes. Okay? So we can draw dependency links between the product of this process and particular roles required to enable these 9 processes. And we can do that for every process in this closed network of processes. And when we do that, we end up with a, just like for the block, but much more complicated, a closed network of mutually reinforcing process dependencies. Now, each of these processes is a specific process, one of these, but to make this diagram a little simpler, I'm just showing them as circles that are colored according to which type of process they are: production, destruction, 1 maintenance, or 0 maintenance. Okay. Now, since we have kind of assumed that there's nothing else in the environment in making this construction, and clearly that's not true. There can be other things in the environment when gliders are operating. I call this the vacuum glider organization. Okay. And this construction I've just described is algorithmic. You can carry it out for any persistent bounded entity in the Conway physics. And then its details ought to be easily adaptable to emergent entities in other cellular automata kinds of models. So this is not unique to the game of life, this construction. However, there is a limitation here that I want to draw your attention to that has to do with the fact that this is a vacuum organization. So this just redraws the force cycle and the derived vacuum glider organization. And I want to point out a problem to you. Suppose we turn on this cell, which is in the surrounding environment of this glider. So this is a simple kind of non-empty environment, right? That plays a role in triggering a process, which is this process, that is different from the original process that we put here. Okay. Its effect is the same. I'll get to that in a moment, but it's actually a different process because it's got different triggering conditions. This process requires this cell to be on. This process does not require this cell to be on. Okay. So that means that whatever node in this graph represented that process has to be removed, and we have to now put in this process, okay? Which means that this no longer describes all of the possible instantiations of a glider. It only ever described a very particular instantiation, namely the vacuum case, the glider in an otherwise empty environment. However, I've already kind of pointed this out, but it's relatively easy to check that whether that cell is on or off, the glider goes through exactly the same set of configurations as it did. So it goes through the same set of configurations when that cell is on as it did in the vacuum organization when that cell is off. So clearly, whatever this organization defines has as much right to be called the glider organization as the vacuum glider organization. Okay? And so we need to amend our definition of an organization in order to capture the full generality, the full range of conditions under which a glider can persist. And to do that, I need to extend this notion of a process into what I call partial processes. So here are 4 examples of a process, one of each type, all of which share the same states in this L-shaped triggering region. Okay, but they differ in the triggering requirements of the other L shape. In addition, this pair of processes both have the center cell is currently off. And essentially, depending upon what's out here, this could be a 0 maintenance process or it could be a production process. In this particular case, when this cell is on, this will be a 0 maintenance process. When this cell is off, it'll be a 1 production process. Likewise, this pair of processes could be either a 1 maintenance or a destruction process according to whether that same cell is off or on. And what the points I'm making here are not special to these 4 processes. There's actually a whole set of processes that have that property, that they could be a 0 maintenance or they could be a production process. They have the same L-shaped triggering conditions, but they have different conditions here. And likewise for one maintenance destruction. Okay. So the problem that we have with this notation for processes is that it's too specific. It completely spells out all the triggering conditions. It's a reaction that will only take place when all of the necessary conditions are satisfied. And what we want to do is actually try to produce a notation for processes that can talk about sets of processes, all of which have the same effect. And to do that, we introduced this notion of a partial process. Okay, so here, a partial process, the gray cells are fixed triggering conditions. Okay, so notice the L regions here are all the same. In this partial process or this partial process, the L region is fixed. Okay, yellow locations basically specify triggering conditions whose current value we do not know. And I'll show you why that's important in a moment. But for now, they're just unspecified. They're not don't cares, because as we saw, it matters how you fill them out as to what happens, whether this process becomes a zero maintenance or a production process, for example. And the split in the middle basically says that depending upon the states of these triggering conditions, this could be a zero maintenance process or it could be a production process. And what determines which it is, you can derive right from the Conway physics, has to do with the sum of the values of these cells. When that sums to 1, then this will be a production process. And when it sums to any value other than 1, it will be a zero maintenance process. Likewise, here for one maintenance or destruction. Okay. So this lets us now have a notation to talk about sets of processes that have the same overall effect. And what I want to show you next is that that allows us to derive a generalized glider organization which applies to all conditions in which a glider can persist, not just empty environment conditions. And the first step in doing that is replacing the boundary processes of a glider with partial processes, because some of those triggering conditions depend on things outside of the glider. They depend on the environment in which the glider finds itself. Okay. So these all become partial processes. The internal processes are still total processes. They're still completely specified because they're surrounded only by fixed arrangements of components that exist in a glider. Okay. So let's pick one of these. I'm going to start with this one and look at what happens now with these partial processes. Before, every total process just specified a component that then played a role in the next set of processes. But these partial processes are going to be conditional on the sum of the yellow cells. This one is trivial. There's only one yellow cell, so it just depends on the value. But some of these other ones have multiple yellow cells, and it will be the sum that matters. Okay, so we can state the condition that will allow this set of processes to transition to the appropriate next set of processes in the vacuum glider organization by saying that we want this to be a zero maintenance process that will play a role in this set of processes. And for that to be true, the sum has to be not equal to 1. That is, this cell has to be 0. Okay, so that's a way to say any process for which this is true, and there's only one in this case, but again, in some of these, there are many, many processes with different combinations of yellow cell values, which will serve the same role as the vacuum case did. In particular, remember, this was the problematic one previously. This has now been generalized so that anything, any combination of yellow values here, as long as they sum to the appropriate number, can play the same role as in the vacuum case. But okay, now we have a new problem. What if this constraint is violated? Okay. Well, if this constraint's violated, what turns out to happen is that this becomes a production process when this sums to 1. And when we look at the role that the components that get produced by this process plays, what we find is that it triggers this set of processes in the second step of the normal glider cycle. Effectively, if we violate this condition, we skip ahead one step to the glider configuration, but we remain in the same organization. Okay? Since this new set of dependencies was not part of the vacuum glider organization, that forces us to extend the organization in a fundamentally new way. But we're still not done. Consider this situation. Here is another partial process. I'm focusing on the production branch of that partial process, and which will be triggered when the sum of the yellow cells is 0. And it turns out that that supports both the one-step or the two-step glider configuration. And which one is actually adopted depends on what happens with the other processes. Okay? But we still here have a situation where, what if this constraint is violated? What if the sum is equal to some other value than 0? Well, it turns out that those sets of dependencies will trigger something else. And what? It's another configuration of these processes that still make up a glider. Effectively, what happens is there are four cycles that a glider can adopt. This was the vacuum 4 cycle, and we're generalizing it to show all the non-vacuum situations that that same 4 cycle can persist. But these other 3 4 cycles are different from the vacuum 4 cycle. And the conditional processes in the vacuum configuration trigger other processes. So here we're not just skipping ahead in one 4 cycle, we're actually jumping to a different 4 cycle, which nevertheless is a glider and persists as a glider. Okay? So once again, we've had to fundamentally extend the glider organization that we derived from the vacuum case. And we can keep doing this. Here's an intermediate step where I fleshed out some more of these possibilities. You start to link up all 16 of these different sets of processes into one big process dependency network, and which path you go down through that network depends on the particular environments in which the glider finds itself. The special case of the vacuum pattern only occurs here when all these sets of interdependencies are satisfied and none of them involve jumps to other branches. Okay? So if we work that out completely, and by the way, I'm not showing the constraints anymore. There's going to be a condition on each set of these processes, which I showed you earlier, but it gets messy to write that out in this diagram, so I dropped that. But it's still there. The fact that this goes one way or another depends on that condition, on the sum of the yellow cells. So if we work that all out, we end up with this dependency network. So this is the generalization of the vacuum glider organization. And this describes conditionally on the environments in which the glider finds itself, all of the different situations in which a glider can persist. It no longer requires a vacuum state. Okay? So let's think about what happens here. Okay? This is a diagram taken from not Maturana and Varela, but I think it's Luigi, a paper by Luigi about autopoiesis, which says that one way to think about autopoiesis is kind of a closed loop where we have some bounded system whose operation generates a network of processes which produce components in configurations that determine the original bounded system. So let's see how the glider maps onto that. Clearly, our bounded system is this arrangement of components, or another version of it, which we'll talk about later. When you put that arrangement of components together under the operation of the chemistry, the Conway chemistry, that's defined by the Conway physics, that produces a network of processes whose general form is captured by this generalized glider organization. And the operation of that network of process interdependencies generates a set of components. And it doesn't just generate them, it also generates them in a spatial arrangement that actually determines exactly this bounded system. Okay, so like the self-producing factory, the factory that makes itself, you can see that through the operation of this configuration of components or this network of processes, we continually regenerate the same identity, the same network of processes, the same, excuse me, the same compact, bounded, persistent arrangement of components. Okay. Now, one common misunderstanding of autopoiesis is that it's completely closed off from the environment. Okay. That's not true in multiple ways, but let me point out in general, if this loop operates in the physical world, not in the Conway physics for a moment, then clearly to make this loop continue requires importing matter and energy. You have to drive this system away from equilibrium, and it produces waste products. Now, gliders turn out to be a special case of these entities in the game of life that essentially can operate without any external events occurring. That's why the glider organization exists. I'm sorry, the vacuum organization exists. A glider can persist in completely isolated from its environment, but that's not generally true, number one. And number two, as we will see, when gliders are in non-empty environments, that can affect the way in which they move through this network of interdependencies. So you can have essentially gliders taking actions, I'll say it that way for now, in a way that depends upon the way the environment affects them. And they in turn affect the environment through those actions. We're going to get to that later. So the main point is that we basically have this autopoietic loop going on in the Conway physics and the Conway chemistry that autopoiesis prescribes, and that it's not completely sealed off from the environment. Okay, how much time do I have? What I want to do now is very quickly talk about two applications of this idea, now that I've defined it, and then I will wrap up and we'll begin our discussion questions. Okay? So I'm not going to go through these applications in detail, but I just want to point out to you that once you have this rigorous definition of, say, a glider organization that you can compute algorithmically, then you can start applying it to things. You can start using it to calculate other things. And one of the things that we've done with this generalized glider organization in a recent paper from last summer was we showed how you can calculate a glider's intrinsic viability constraint. In biology, we often talk about viability constraints. That is, the sets of, well, normally it's the sets of essential variables that have to be maintained within some viable region in order to, for that individual to persist. And if you violate those essential variable constraints, then the individual dies. It dissipates. It becomes just chemistry or just physics, no longer biology. Typically, those viability constraints are imposed externally in theorizing in biology. That is, I say, here's my model E. coli, and if the outward pressure on the membrane ever exceeds some threshold, then I'm going to say the membrane has burst, and therefore my model E. coli has died. Okay. But in fact, in biology, we don't get to specify the viability constraints of an organism. They arise intrinsically from, in Maturana Varela's terms, from that organism's organization, from the particular way in which its operational closure maintains its persistence, maintains its identity. And so from that generalized glider organization, we can actually calculate the intrinsic viability constraint of a glider, which I'm showing schematically here, consisting of an interior, which includes roughly 183 trillion configurations in this space, and a boundary that consists of about 143 quadrillion configurations. And of course, I'm only showing a few samples of the interior and the boundary, and every other configuration of this grid that doesn't fall within the interior or the boundary is not a glider. And that's not an arbitrary statement. I don't just say, well, I want to call that a glider, and I'm not going to call that a glider. This is calculated from the glider's generalized organization. So that organization, that network of dependencies, determines what falls inside this viability constraint and what falls outside of it. Okay. By the way, these numbers I just roughly quoted to you can be computed exactly from the construction that we do in this paper. So that's one kind of application. There's a whole story to be told there, but I just wanted to put it out there before I run out of time. The second application, which directly feeds into the topic of this school, is we can inquire into the origin of gliders. That is, we can say, okay, if gliders are sort of like biological systems in this toy model, I'm not saying they're anything like biological systems in the real world, but with respect to this theoretical framework that Maturana and Varela put forward, and my particular fleshing out of that framework into a rigorous theory, we can think of gliders as kind of biological individuals, and we can ask questions about their origin. Okay? So one way to do that is we can do an experiment. Suppose we randomly generate universes with zeros and ones in some tunable density. So I can randomly generate a universe configuration that has a 1 in 100 chance of any individual cell being on. Or I can generate such a universe with a 90 in 100 chance of any one cell being on. And I can track, like this one right here, or this one there. You see these gliders appearing and disappearing. Okay. So I'm starting from configurations that generally do not have gliders, and gliders come into existence. They persist for a while, and then they disintegrate. So I can do that experiment. I can do it millions or billions of times. What I did for what I'm about to show you is I did a bunch of different one density values. For each one, I did a sample of 10 to the fourth initial conditions per density value, and we can just plot that out. So here shows over time, and the vertical axis here is the one density. So if I start out with a one density of 0, that is, there are no ones, then no gliders ever appear, okay, because there are no one components. And if there are no one components, all the processes are null processes, and null processes cannot produce anything that would be required to make a glider. Likewise, if I start out with a density of 1, every cell is on, then no gliders occur. Okay? But there are these intermediate values of P in which gliders do occur. For these values, they occur very quickly. For these values, it's hard to see, but they actually occur in the initial population. And then they evolve in some way. There's some epoch of time where gliders come into existence, they proliferate for a while, and then they are extinguished. Okay? And another interesting feature that we see here is that there are two particular bands of one density that if you start with universes in those bands of one density, then you get gliders that persist forever. All I've done here is multiply the values by a factor of 5 so they brighten up these bands of persistence. Okay? So there's all kinds of interesting statistical structure in the way gliders appear, proliferate, and ultimately are extinguished. Okay? Can we develop a theory of that from the way gliders work in terms of their organization? Well, we did, and basically, without going into the details, what we did was develop essentially a statistical mechanics of gliders in terms of density creation, persistence, and destruction operators. So if you have a glider density at some time, say T0, with a given P, that is this value, then the density at time 1 is going to involve the density creation operator and the density destruction operator, or the persistence operator and the creation operator. These two are equivalent, since what persists is just going to be the difference between what's created and what's destroyed. Okay. So anyway, we can write equations like this. We can define these operators. That's what I'm not going to do here, but you can mathematically derive these operators. And then you can apply them to decomposing essentially the statistical mechanics of gliders over time. So at t equals 0, you generally don't have gliders unless you're in a fairly narrow range of one densities, and then you can have gliders. Over time, creation, destruction, persistence, and so on occur in particular patterns. I'm not going to go through all of this, but notice that you get creation typically at these extremes. You get these two humps, but that eventually the creation at the humps stops, and you get creation exceeding destruction in the middle, and this valley rises over time until you get to a particular value about time equals 60, when creation and destruction operators are balanced. And then beyond that time, the destruction operator dominates the creation operator, but only by a tiny bit, so that over time, this long mesa falls. That's what's going on here, until in the end, you're only left with these two little peaks of glider persistence. That's these two bands. And it turns out, again, I can't go through this, but in the general statistical mechanics of the game of life, not the statistical mechanics of gliders, but the general statistical mechanics, it turns out that those two regions where these peaks occur are special transition, they're phase transition regions in the statistical mechanics of the game of life. And you're seeing those play out in the glider dynamics here, okay? So again, really quickly whipped by here. I know there's more that you can do with this, and I haven't shown you any of the details, but this is another example of the kinds of things you can do now that we have this at least sketch of a theory of constitution grounded in autopoiesis for what a glider is. So far what I've done, and I'm wrapping up now, it looks like I'm right on time, surprisingly. I can't promise that'll be true for both lectures. So what I've done is taken a very simple physics. Again, it's not real physics. I don't want to overclaim this at all. It is a toy model universe, which is simple enough that we can calculate, we can build theories and calculate things with those theories about questions that we simply cannot do yet in the physical universe, okay? I've shown you how that physics works. I've shown you that it supports an underlying spatial chemistry, and that spatial chemistry can produce ephemeral or persistent networks of processes that satisfy an interpretation, let's say to be precise, of Mataran and Varela's notion of autopoiesis, which is a suggestion that they've made, an organizational suggestion, as to how one ought to think about what constitutes a living system. Not a list of its components, not a list of its characteristics, but rather a statement about its organization, about the interdependencies of its underlying processes. Okay? And I think I will stop there. I have some discussion questions because I was asked to provide them, but I just as soon start with questions from the audience. And if that peters out, then I can throw up some of my discussion questions.
Thank you, Randy. Thank you. So now we have some time for questions before Randy will provide some discussion questions. Anyone want to ask something?
Does this model can reproduce anything from real life?
Well, again, it's a completely different physics, so it depends what you mean. It can produce the persistence of individuals that are fragile, that without the particular structure of autopoiesis wouldn't persist, according to the Conway physics, according to the underlying laws of physics and chemistry. It possesses an intrinsic viability constraint, which one can derive. One can investigate questions of origins, and one can talk about interactions with these entities and their environments, which is what the next lecture will be all about. If you're asking me, if I put E. coli in this particular situation and ask, what does this model tell me about what E. coli will do? Then of course not, no. That's not the purpose of a toy model like this. That would be the purpose of an empirically grounded model of, for example, E. coli, which people build.
Hi. So I'm very impressed on all the theoretical building that you've shown. So my question is that fluctuation seems to be essential for real life, and if I understand correctly,
I'm sorry, what does?
Fluctuations, random fluctuations.
Yeah, thermodynamics, basically.
Yeah, but
Yeah.
in this toy model you have completely deterministic evolution, right?
That's correct, yeah. Although
So-
there is a statistical mechanics one can derive for this. It is, I mean, let's see. Yes, I understand exactly what you're saying. It's actually one of my discussion questions. There are a couple of ways I could push back on that. I mean, first blush, you're absolutely right. That's one of many things that this model does not incorporate. A couple of things I can say. One is that, at least classically, classical field theory is also deterministic. Thermodynamics only comes in when you entropy and all statistical mechanics, all this stuff only comes in when you impose limitations on what the scientists can actually measure. That is when you start coarse graining things. If you had in a classical theory, if you had complete access to the underlying states of the field, say in net theory, then it's all perfectly deterministic. Okay. And if you can do the same thing in the game of life, effectively that's what we do. If you coarse grain, so you don't talk about the states of all of the cells in the entire universe, you say there's some density of gliders. That's a coarse graining. Now you can't uniquely predict what the state of the universe will be. You can only predict what the density properties will be. And that's the same sort of thing that happens in thermodynamics in the real world. So that's one possible response. Another response is that you could add such a thing to the Conway physics. And people have done this in a couple of ways. One really simple way is you can add a temperature to the Conway physics, to that dynamical law, so that the transition becomes probabilistic. It's not just dependent on the sums and the current states. It also has some Boltzmann-like term that's temperature dependent. Okay.
Thank
A
you.
third kind of answer I can give, and then I'll stop. These are ideas that you can. Also in the vein of that second one, you could drive the game of life. This is something I proposed a while ago. The game of life, as it's described here, functions purely autonomously in the dynamical system sense of an autonomous dynamics. But you could, so it's a closed system, but you could make it an open system by driving, say, one corner of this universe with an influx of one cells. Okay, that pushes it away from equilibrium. And you can start to get far from equilibrium kinds of phenomenology in the game of life. There are new kinds of persistent structures, for example, new kinds of quote unquote biological individuals that develop in those far from equilibrium conditions. So that's two. And the third and final, the third and final response is that we often think about the far from equilibrium nature of a requirement of life in the real world as a plus. But here's an argument, it's actually a minus. Basically, because of the thermodynamic nature of the real world, we have to work really, really hard to build codependent networks of process dependencies. Okay, so it's a problem to be solved to get back to the situation that we already have for free in the game of life, in the Conway physics, which is that we can build and explore these process dependency networks without having to work really, really hard. We don't have to, we can, but we don't have to push the system far from equilibrium. Okay, so those are all, again, you're not wrong. I agree with you. It does not cover in any direct way the thermodynamic characteristics of the real world. But there are various arguments for why that might not be a bad thing, at least to get started. Or you could push this model in the direction where you might explore how to incorporate those things in various ways.
Great. Thank you.
I have a question that's about the thermodynamics of the model as well.
Well, this model has no real thermodynamics. It does have a statistical mechanics, but
Yeah,
anyway,
but
go ahead.
how would you go about energy consumption? Because from the where I see the glider is self-sustaining, and
Right.
it's not dependent on consuming what's
That's correct.
around it. Like
Yes.
there's no
So,
metabolic maintenance for that self-sustainment.
that's right. There's not. I mean, that was the previous question's point. There is not. However, I mentioned very briefly that that's a property of the glider. You can imagine, and maybe design, I haven't done this because that has not been my focus, but it would be an interesting experiment. You could imagine that there is some persistent entities that only persist if they continuously consume some stream of structured environment configurations. Okay, so as long as, for example, they're gliding along a string of these environment configurations that have the right structure, they continue to persist. Whenever they run out of that stream, they fall apart. So unlike a glider, which indeed does have a vacuum persistence capability, that entity would not. I don't see any reason why such entities couldn't exist in the game of life. Do I have one to show you? No, because I haven't focused on that. But I don't see any reason why particular external interactions with the environment, effectively consumptions of one cells, would be required at key points in the cycle to allow that individual to persist. And if one were interested in pursuing that route from this toy model, that would be something to try and discover such configurations that have no vacuum persistence. They only persist in environments that provide certain kinds of structured material for them to work with.
Yeah, Randy, I have a question. So you're assuming that the word is discrete. So you think the word is discrete or continuous?
That's correct, in multiple ways. So this cellular automata is both discrete space, discrete time, and discrete state. Okay, you could relax any or all of those things. And in fact, I have a student who's finishing up his thesis right now that looks at removing the discrete space component. So he's looking at how you would generalize these ideas to cellular automata, or almost really reaction diffusion type systems. But they still have discrete state, they still have discrete time, so they're not pure reaction diffusion, but they have continuous space. So it looks like it can be done. It's mathematically very complicated. I can talk a little bit more about what's involved in doing it, but yes, so far this is all done in a discrete case, and there's a good reason for that. Combinatorics is almost always easier than analysis, mathematically speaking. Okay, so it's easier to work with discrete structures to define like this graph of process dependencies. What does that turn into when space is continuous? Well, it turns into some continuous analog of a graph called a graphon. Okay, and working with graphons is mathematically much more complicated than working with graphs. So it can be done, but the math gets more complicated. And I am a big fan of working things out in the simplest case first and then complicating, rather than saying, well, all these things are important. I really have to start with a toy model that includes them all, which often makes it impossible to even get off the ground.
Thank you, Randy. I have some questions. I don't want to dominate, but I'm very curious with at least two questions. So I love your analogy with the factory, the self-sustained factory. But I wonder, in your game of life model, what would be the equivalent to waste, actually?
So again, the glider can persist without taking anything in and without producing any waste. Okay. In non-vacuum interactions, gliders can leave stuff behind. And if you imagine that entity I mentioned to one of the earlier questions that depends on some stream of available organized one components to persist, they can also leave waste one components behind. And there are known game of life entities that leave stuff behind as they move. So producing waste is not difficult. I don't know of anyone off the top of my head that actually persists the way a glider does, except requiring a constant inflow of organized material from the environment to do so. I don't think that's a question anybody's ever posed in the game of life, because nobody else has ever looked at game of life as to whether or not it supports autopoiesis.
I see. The other question that it's a little bit more, let's say, philosophical question. So I wonder, like, for example, you start with a definition what would be something that is you would consider bounded system, right? But that is in some sense subjective, right? It depends on us to define what is a bounded system. So it's not an inherent definition. So
Yep.
in some sense, there is a little bit of this circular argument in this entire argument about life, about autopoiesis. You know? So I wonder that how you would, if you consider this as a problem, or if it's inherent to what we consider as a life.
I think it's inherent to the way science works, not just life. What I've tried to do is basically be a scientist in the Conway universe. Okay, when we as scientists look at the natural world, we don't typically focus our attention on spatially and temporally distributed systems. So, the color of a bird's feather in Brazil is one of my states, and the sound that some vervet monkey makes in Africa is another one of my states. And I take together all these weird spatio-temporally distributed states, and I package them together and say, that's the thing I want to understand. Usually, the first act we do as a scientist is we look at the world and we say, that's interesting. That's a thing I'd like to understand. And when you look at the game of life, from random initial conditions, these persistent localized structures are the first thing you notice. They pop out, they're localized, they're compact, and they're persistent. And I would argue that it's also the case that we generally do the same thing in science, is we're on the lookout for compact, persistent structures. And it's those that we turn our attention to. Now, as you may know, I've completely ignored, and I may briefly touch on this in my second lecture, there's another whole component to Maturana and Varela's biology of cognition, which is basically the role the observer plays in that theory. Okay, so what Maturana did originally was he actually made that role explicit. Normally, we leave it implicit in science. We don't think about that act that we do as scientific observers to carve the world up into things we want to understand. But he brought it front and center and said, that's a part of all science, and we should be explicit about it. And in the end, the job of a theory of cognition, he argued, was to explain what an observer is, so that we can postulate the observer and then explain it away, explain an observer eventually once we have a fully developed theory of life and cognition. Now, that is a circular activity, okay? And again, if you're familiar with Maturana Varela's biology of cognition literature or the subsequent inaction literature, it's filled with those kinds of circularities. I think if you think carefully about it, those circularities are inherent in how we operate as observers, and in particular as scientific observers in the world.
Yeah, I totally agree with this circularity. It's always appear when you try to understand some biological world. But just to go to the the consequence of this observation is that in principle you couldn't there is not a unique way to define life in this sense. Right? You choose what's your object, and you just check if there is all these property that you were discussing.
Yeah, I mean, the same thing is true in the real world, right? I mean, take a virus. A virus is this thing. It's a compact, persistent entity. And there are debates as to whether or not a virus is alive. Okay? Those debates shift around over time. You could adopt one or the other. What I would say is what I said at the beginning of this lecture, and what I just said now. If you as a scientist look at a universe, okay, typically the real universe, but I've shown you a toy example of this here, you carve out things that are interesting. Okay, you want to understand something about those things. If what you want to understand is that thing a biological individual, I've argued that you can't answer that question unless you also adopt a particular theory of what a biological individual is. You can't just say, well, my gut feeling is it's alive, or my gut feeling is it's not alive. No, you need to say with respect to some theory. And what I've tried to do is show you that certain entities that scream out at any observer of this toy model universe can be considered to be biological individuals according to a certain theory, namely a somewhat rigorously formalized version of Maturana and Varela's notion of autopoiesis. Okay, if you replace that theory with a different one, like a list of characteristics, one of which is reproduction or evolution, then you would reject the idea that these entities in this toy model are biological individuals because they do not reproduce or because they do not evolve. Okay, so it's always a relative assessment. It's relative to the entities you've picked out as a scientist to study, and it's relative to the particular theory that you bring to bear on those entities that you commit to say, this is what I think a living system is. It is a certain organization. It's a list of characteristics. It's a list of components, or so on.
Perfect. Okay, so there's one more question, and then maybe we can move to the discussion topics. Let's see.
Sure.
Does the tessellation of the system affect somehow how those living things appears? And like if you do it also in 3D, would it have like similar dynamics?
No, the dynamics would be different. The question would be, and it's an interesting question. I think I know what the answer would be, but I haven't done it, so I can't be sure. You'd have to see if, well, certainly you could define an analogous chemistry that I have. If you look at 3D life, which is, it's a thing. People have extended the game of life to 3 dimensions. You could produce a chemistry that would now have a triggering, say, cube of configurations that would be your reaction networks. You'd still have dependencies between components in that cube and the processes they trigger, and therefore between one process's enabling conditions and another process's products. So you could certainly define networks of dependencies in that case. Then you'd have to look at whether or not these closed networks of dependencies underlie the persistence of whatever entities you've singled out to be worthy of study. So, I mean, that's a research program. You could carry that out. I won't presume to claim how it would come out, but I don't see any reason why it would be any different in kind to what I've shown you here. It would just be more complicated. And certainly the organizations and the entities that you get are not the same. But their closure, the closure of a dependency network, is still going to be the thing that underlies any persistent entity. It still underlies, when we generalize to continuous space, I referred to this work that I have a student doing, the same ideas apply. It's just that how we mathematically describe these dependency networks gets more complicated because we can't talk about discrete graphs anymore. We have to talk about essentially continuous graphs or graphons.
Great. Thank you, Randy. So maybe we can move to some discussion topics that you have prepared. Yep.
Yep. So here are a couple of ones I came up with. We've touched on some of them already.
Okay, anyone has some comments on some of the topics here? So there are, let's see, why begin with physics rather than direct at biological level? Okay, is a glider alive? And what does any of this have to do with biology? Okay, there's a lot of overlap with our questions.
Yeah, that question has been asked.
So, okay, so maybe we can just, so what's missing from this toy model? Anyone would start with this?
Well, that's already been answered in part 2. One person suggested thermodynamics, and that's very true.
Sorry, what's that? Sorry, Randy, I didn't hear what you just.
Oh, I'm sorry. I said one person suggested thermodynamics was
Yes,
missing,
okay,
and that's
so
certainly true. So
yeah.
we've already got one item.
So let's start. So I think for me, one thing that seems to be missing, if I understood correctly, is that in life sometimes you have also these long range interactions, right? And in this game of life, for example, I can see that, for example, the sun interacting with the whole life on Earth. Right? So there's a long range the interaction that doesn't seem to appear in this game of life thing. It seems to all the interaction seems to be quite local in this respect. So I wonder if this has a big effect in this general theory of life.
So let's think about that. Again, in classical physics, I'm not talking about quantum physics and entanglement, that's a different issue. But in classical physics, every one of those long-range interactions is known to be mediated by a chain of short-range interactions, right? So that light that you see from a distance is actually a photon hitting your retina. It was emitted by a very distant source, but it had to travel across all that space and in the time it took to travel until it actually underwent a local interaction with your retina. And that's the same thing in game of life. Again, interaction is what we're going to talk about next, but you can imagine that something happens across the universe and it generates propagating structure across the intervening space such that sometime later that interacts with the glider. I would argue that that's exactly the same situation. It's only if you have a truly non-local interaction, like entanglement in some ways seems to be in quantum mechanics, that you're absolutely right. This is a classical toy model. It's not a quantum toy model.
Hello, Randall.
Yes.
You talk about viruses, and I was thinking that in this game of life framework, we can postulate that a virus it's as alive as a glider in the sense that it maintains its structure on time. And my question is, in the general framework of Maturana and Varela of autopoiesis, do you think that it postulates that viruses is alive?
I don't know where they would come down on that. I mean, normally the argument for a virus not being alive is that it has no metabolism of its own. It's essentially a genetic structure that depends upon some host cell for actually the metabolic components. So I would think the way to answer that question would be to ask if there's any analog of that in this toy model. And one thought might be, so these static structures like blocks and things, you could think of them as frozen structure that when they come into contact with something like a glider can co-opt that process network in order to do something that the static structure is unable to do itself. That's a little bit tricky because, as I showed, it seems like even static structures can be thought of as a kind of process network. So you'd have to impose some additional restriction, like you have to have a longer cycle than a one cycle. So you have to have something that isn't just static, that just generates itself directly. It has to go through some set of steps that generate itself. And that you're not going to call a metabolism something that is a one-step regenerator. In a sense, that's just physics. So yes, I mean, it's a tricky issue. I don't know how I would answer it. I do want to stress that this toy model is not the one true perfect toy model. I'd be very happy if people proposed a dozen other kind of toy models, which made different cuts than I did, and tried to apply, doesn't even have to be autopoiesis, some existing theoretical framework as to what a living system is, or what behavior and cognition are, which we're going to get to later in this framework, in the next lecture. I don't want to be seen as suggesting that this is the one you should use. I think it has certain things that recommend it as a good starting place, namely that it's almost minimal in its simplicity. You can't remove much from it and still have this range of things that we've been interested in talking about. It also, the one reason I picked Game of Life is it's a highly studied cellular automata. There are, an infinite number of cellular automata, but there is no cellular automata that's been studied in depth as much as the Game of Life. Okay, but it's just a starting point. I've been amazed at how far I've been able to get between what I've talked about today and what I'm going to talk about after the break. How far you can get with just this minimal model, but clearly, it's got limitations. I've reached those limitations in a number of ways, and to go forward, you need to look at ways to complicate this toy model to incorporate other features that we care about in biology that aren't well captured here.
Thank you.
So, just one last question here. Sorry,
Sure.
I was curious for your last. I'm Danny here. So, for your last
Yep.
application, so
The origin stuff. Yeah.
from the entropic point of view, do you see that there was some like a transition from the disorganized kind of situation to more organized, and then it will keep in this more organized situation, or actually there was a lot of fluctuation around?
Yes, in both cases. And in fact, the equilibrium state of the Game of Life is one of organization, not disorganization. Essentially, the quiescent state, the empty universe, is a massive, massive attractor. I think I have some slides that will show that more in the second lecture. But so there's a tendency to organization, not disorganization, which is one of the big differences in the statistical mechanics of the Game of Life versus the real world. That's not necessarily true when you take driven Game of Life. So when you make it an open system and you drive structure into it, then things are a little more realistic thermodynamically, although whether they're fully realistic, I think remains to be determined, and probably the answer would be no. But I think that's a step in that direction.
Mm-hmm.
So yeah, there are actually statistical mechanics people who have studied the Game of Life as a system in which to apply statistical mechanics to. Not gliders. That was something we did new, but well before we started looking at this, there are in statistical physics journals, you can find papers on the statistical mechanics of the Game of Life and phase transitions in it and so on.
That's very interesting. Okay, so I think we can go to the coffee break now, and then we come back at 10:45.
Okay.
Thank you, Randy.
Yep. Sounds good.
Thank you.